Hello again. In this lecture, I'd like to talk about what I would characterize as unquestionably being one of the most important analytical tools that's used in all of material science. And I'm talking about the applications and utility of scanning electron microscopy. We're going to cover a number of different ideas in this lecture, which will be presented in two parts. We'll speak first about the design and operation of an electron microscope, and in particular the detection elements that render the ability of electrons to capture topological and important compositional information about a material sample. And we'll understand analytical attributes associated with how these kinds of measurements can be made on both conductive and non-conductive samples. And we'll also talk about some more complicated analytical applications that are possible within an analytical secondary electron microscope. In your reference materials, there will be slides on related techniques, in particular the combination with focused ion beams, although they will not be discussed in today's lecture. So first and foremost, what does an SEM do? An SEM largely takes pictures, but not with photographic film, but via the interaction of an electron beam with a material surface. We can obtain information about the topological characteristics, surface morphology, and in very powerful ways, information about the composition of a material. This is a measurement that is fundamentally not a surface analytical measurement, but it is in fact one that is very much capable of producing topological characterizations, and that is, profiles of height, depth, and in correlated forms of measurement, issues related to composition. An electron microscope, by definition, uses electrons as a probe. And similarly, most analytical applications uses the detection of electrons as the fundamental measurement protocol from which all the information is derived. And because of the fact that we're using electrons, it has very high spatial resolution, typically of the order of several nanometers to tens of nanometers for the most powerful and modern analytical microscopes. But it also can measure other properties. So where electrons generate electronic excitations which lead to the emission of X-rays or light, those are the forms of secondary analyses that can also be coupled within an analytical electron microscope and provide other forms of information. It's useful to compare electron microscopy to other forms of microscopy, in particular microscopy used with light. We know first and foremost, because of the difference of the wavelengths involved, that the spatial precision, but mostly because of the beam diameters involved, the spatial precision of an electron microscope can in fact be very high compared to optical microscopy. But the other part of it is that because of the way the optics work, it has remarkably enabling attributes with regard to field and depth of view. So we can see two representative images, one acquired using an optical microscope, the other acquired using a more conventional SEM instrument. And you can see the higher resolution and depth of focus that one obtains for this imaging of I believe these are, well, I don't know what these are. These are pollen spores, or perhaps the disembodied remains of sea creatures, but small microscopic organisms. But you can see that, in fact, the very high spatial resolution that's afforded with the use of electrons as the imaging probe. Okay, so how do we acquire an image? Well, first and foremost, we use an electron beam as the primary interrogator of the material surface. So an electron microscope will have an analytical column which defines all the features associated with how we get electrons into the sample. So this is the sample region at the bottom. Because we're using electrons and because of the fact that electrons interact very strongly with matter and there's large distances involved, this is all a vacuum environment. And because of the fact that we're not doing surface analytical spectroscopy, the vacuum environments that are used here, can in fact be relatively less demanding than is true of techniques such as XPS or AES. They can be high vacuum environments, to the order of 10 to the minus 5, 10 to the minus 6 torr are perfectly adequate for these kinds of features. And then what we do is we scatter electrons from this sample, and we have a secondary electron detector, which is shown here, which then images those electrons. And then as we interrogate a sample point by point, we then take those electron intensities that are read at the detector, plot them point by point, and we have an image. Okay, this shows a broader a more detailed description of that. And part of the things that I will point out is that much as would be true with an optical microscope, electron microscopes always use compound lens elements, right? So for example, you have different kinds of magnifications that are possible. And we'll see more in the next set of lectures when we cover transmission electron microscopy. It's via compound lens elements that we get to very high analytical resolutions. But this shows a two-stage lens system, condenser lenses and an objective lens that's used to provide a precise, narrow diameter beam at the sample, which is then steered and rastered across the sample, and then via detection of the electrons reaching a secondary electron detector, or then through the data system used to construct an image. Okay, and then the other part of it is that we have a way of introducing a sample into the vacuum environment and rotate it and otherwise move it with respect to the beam elements. This shows, two conventional kinds of SEM instruments, both of which that we have in our analytical laboratories at Illinois. This is, and part of what's really nice about secondary electron microscopes is these are really accessible instruments. Everybody in an afternoon can learn to use one. They're very forgiving for the most part. I mean, there's dumb things you can do to very much break them. But largely speaking, these are very much hands-on instruments that students should and can use if they wish to become, expert practitioner in the areas of materials. So, and the sample preparation is actually fairly easy. Sometimes it may involve coating the sample with a secondary material to dissipate charging characteristics. The electron beams that we use are relatively of modest energies. They can vary from 1,000 up to 30 kilovolt beam energies. Vacuum can be very low, and it's good to have it very low in the area where the electron beam is generated. But typically in the sample region, that would be of the order of 10 to the minus 5 torr or so. Does not have to be UHV. And here's a real student sitting in front of an SEM actually working it. This is a fairly capable one. That's a Hitachi instrument that's actually a very high quality analytical microscope. So the major beam parameters that are important are ones related to beam diameter, which fundamentally impacts what the spatial resolution is. The probe current, because we very much care about the rate at which we're injecting electrons into and impacting them on a sample. One of the angular attributes of the beam, not only what its beam diameter is at the focal point, but what its beam divergence is, because that has a lot to do with the depth of the depth of view that one can obtain. And the other part that's actually fairly important is the accelerating voltage. And we'll come back and we'll talk more about that later. Um, and, uh, and, and, um, and there's other aspects associated with the details of electron optics that come into play, but these are really for, I would say, more of the the expert users, and we would think about these when we want to actually maximize things related to depth of focus or image quality, and features of analytical performance. But I'd say for the interested student, the thing to do is to really get hands-on and use the instrument. Okay. There's actually a funny story here, in the sense that this is a slide that shows you different kinds of sources that are used to generate the electrons that are used in analytical microscopes, and really what they vary in terms of is the beam current that can be provided, and it's also a beam current that has the spatial attributes associated with the electron sources. It's not just that there's more electrons with one versus the other. It's electrons per unit area in the cross section, and you can actually see that from the point of view of electron densities that are provided in the top versus what the total currents are, thousands of nanoamps down to fractions of a nanoamp, but the ones over here being the most high spatial precision instruments, where there's lots of electrons per small unit area. And actually a way you can read the top of this is how expensive the microscope comes to be. Here being very expensive, and here being relatively low performance, but actually very low cost instruments. But and another part of this is that these are very survivable instruments to mishaps that students tend to do with instruments, and these are very much less so. So the funny story is, I always heard people say, I'm going to use the Lab 6 instrument, and I always thought that was the room that the instrument was in, and I finally realized that that's actually the material that's used for the emitter source, and I felt quite stupid about that, but we all start somewhere. So it's probably not as funny to you as it is to me, but anyway. We should also talk about how electrons interact with matter. I've said several times in the course of the lectures that one of the things that's important to understand is that electrons interact very strongly with matter, and has really important consequences for what we see in electron-based imaging. But there's these correlated analytical measurements that we do using electron excitations that are very important to the character of SEM analysis. So what's shown here is a summation of all the things that we can do. I can put electron beams in my narrow diameter, low divergence electron beam, and we saw one of the outcomes is that within a very shallow region of the sample surface and in the vicinity of the primary excitation, we can energy analyze electrons and extract for them the rare fraction of electrons coming out of the sample that correspond to Auger electrons, and that's surface sensitive information. We can put electrons into this and actually look at the aggregate larger flux coming out, the so-called secondary electron flux, and use that to construct an image. And we'll see exactly how that's done in the next few slides. I should also mention that the electrons that we inject into the sample can actually lead to the generation of another characteristic form of electron, which are called backscattered electrons, that actually have other important analytical attributes. The difference between secondary electrons and backscattered electrons is related to the physics by which they're generated, but you see that more in the form of the energy profiles associated with electrons that are in the secondary electron flux versus the backscattered electrons. Okay. The other part that's actually important to understand here is that there's also, in the energy range that's being used, the possibility of affecting electron excitations that also lead to the emission of light, photons. And these can be, very broadly distributed across the X-ray wavelength region, and we've seen that in earlier slides. But we've, in certain materials cases for forms of matter that are very efficient emitters of photons and other energy regions, we can see electronic excitations that lead to de-excitations that emit light in visible and ultraviolet wavelengths. That gives rise to a phenomenon called cathodoluminescence. So these electrons are used to do imaging. These electrons are used to do surface analysis. And these electrons are, the X-rays, are actually used to perform elemental analyses. And the ones here that are emitted at UV to visible to infrared wavelength regions, which correspond to bound states of electrons in a solid, those are actually used to characterize features of electronic structure. Okay, and if we sum all this up, right, basically there's got to be detailed balance that, we can't have more outcome than the number of electrons putting in. So fundamentally, the detectable currents that come from any sort of form of matter have a lot to do with the flux of electrons on the incident surface. And materials tend to partition these excitations across a broad variety of de-excitation or inelastic scattering events. And finally, I should note that there's a lot of energy in, and that energy dissipates into a large sample volume element, and we'll see exactly how that happens. But part of it is that there's also a heat flux that comes from this, which is perhaps the least useful part of the measurement. All right, so this is a plot that shows the electron yield as a function of the kinetic energy, and this is shown at a particular kinetic energy associated with the primary electron beam. And clearly, this will be a parameter which is in fact impacted by the choice of your primary electron beam energy, right? And that we have as our E0, the place where we put electrons in with a particular characteristic energy, and then what comes out of it is electrons. So our primary beam energy would have something on the order of many kiloelectron volts, whether it's 5 or it's 10 or it's 20 or 30. That's an experimentally selectable parameter, and we'll talk about why you might pick one versus the other. But then electrons will come out showing characteristic scattering that's elastic scattering, whereas the electrons have lost no energy. The energy that comes out is the energy that was put in. But some fraction will have quasi elastic scattering, which means that there's energy lost, but it's somewhat non-discrete in its profile. We'll see discrete electron energy loss features. This is the basis of what's called EELS, electron energy loss spectroscopy, if we were to energy analyze them. Typically in an SEM, we do not. A broad hump coming off of that. Auger electrons, we saw the characteristic energies associated with what we would do detection associated with Auger electrons. And then down here, the low energy part, all right, are the secondary electrons. And then you notice that, that's interesting, right? The backscattered electrons are relatively broad distribution of high kinetic energy electrons and a somewhat narrower but very intensely peaked profile of relatively low energy electrons that define the secondary electron components. All right. Typically in an SEM image, the secondary electrons and the backscattered electrons all contribute to the image contrasts that are seen, where typically the secondary electrons might be, in fact, the ones most heavily weighted. Okay, so let's think about what happens when we do this kind of analysis, and actually a very cool experiment that shows that The schematic depiction that I showed you in an earlier slide is one that actually is reflected in the reality of this. So these are simulations to analyze the excitation profiles in various materials as a function of kinetic energy. And here's titanium versus titanium with a 5 keV versus 15 keV beam energy. And we notice that, in point of fact, the flux of secondary and backscattered electrons and X-ray emission, which are all embedded in these profiles, varies with not only material type but also beam energy in a very powerful way. Right, high Z element tungsten versus carbon. Right, the de-excitation profiles are very sharp and narrow in this very dense metal, and much more diffuse in low Z or low density material. Here's actually a picture in cross section of polymethyl methacrylate. It's a polymer. For those of you who don't know its structure, it's a very common polymer, and I'm sure you've interacted with it many times without knowing what it was actually that you might have been working with. But used as very high optical translucency, and and it has many useful many useful properties other than it's just its optical properties, and very easily processed. But for this experiment, it has a really peculiar characteristics, and that is radiation tends to make the molecule fall apart, the macromolecule. What happens is you break carbon-carbon bonds, and the polymer unzips. It just reforms the monomer from which it was synthesized. And in this way, you can actually look at where material was lost and image the places where the excitations are sufficient to induce the breakage of chemical bonds. Okay, and this is that was a 20 keV excitation. You notice that it very closely follows the energy dissipation profile that comes out of these simulations. Okay. So it's a really powerful impact. Now let's go into that in more detail. And what you notice is that there's different analytical depths associated with it. Auger electrons, as we mentioned, are very surface sensitive. Secondary electrons, because they're relatively low kinetic energy electrons, have very high spatial localization towards the interface of the material, right? So that, although not in a surface analytical attribute that allows us to determine compositional information, because we're not energy analyzing the electrons in this case. We're just looking at these low kinetic energy electrons that actually manage to emerge from the sample where they can be detected at a detector. Cathodoluminescence has a particular characteristic skin depth because of the fact that these might be in UV or visible wavelengths. That skin depth will be relatively proximate to the interface, much more so than would be true of the X-ray emission, which emerges from a much deeper region of the material surface. So fluorescent X-rays can be used to do compositional mapping, but it's much more, again, a measurement that's in the extent of a material rather than its near surface or interfacial regions. Okay. So that's a sort of an important thing to keep in mind. So how do we detect secondary electrons? Actually, it's a fairly simple detector, which allows us to pick up, in fact, electrons emerging from the sample from a variety of different emergence angles. And the slide here is showing, if you look at these blue traces, electrons that follow trajectories very much, in the line of the detector, but also ones that have to, in fact, be grabbed by the E field at the detector acceptance lens that actually pulls electrons and drags them back into the analytical region of the detector. So and the other part about this is, so this is a high field that's present to grab electrons and drag them in. And you notice that you see the trajectories of the secondary electrons are drastically altered by this. But because the backscattered electrons are relatively higher energy, fewer of them, other than ones coming from direct line of sight trajectories, make it to this detector and are actually injected in a way that are successfully detected. Because part of what happens is that electrons are pulled in, and at the back plane of this detector, where they enter where they strike a scintillator, and then that light pulse is then amplified in a photomultiplier, right? So we get one electron in and a cascade of electrons out, right? So and these amplification factors might be as much as a factor of 1,000,000, that for every electron in, you get 1,000,000 electrons that eventually are detected as the analytical current on the output. Okay. Now, part of what we have to think about is what's the nature of the secondary electron yield. And part of what this has to do with is that, as we mentioned before, in cases where we're detecting low energy electrons, a lot of it has to do with just spatial attributes associated with how we position the sample relative to the excitation source and the detectors, and sample tilt turns out to be a way to actually leverage both of these impacts in a way that will leverage image contrast in secondary electron microscopy. So, for example, if we tilt the sample in such a way that the secondary electron flux is generated in a spatial domain more proximate to the free surface of the sample, more of those electrons will escape and be collected by the secondary electron detector, right? So sample tilt turns out to be a way of very powerfully impacting the detectable currents at the secondary electron detector. But it also has the effect that it scales the spatial depth sensitivity that you're collecting electrons from. So typically the skin depths for these electrons are going to be of the order of nanometers, right, to tens of nanometers. So you can see we're looking at the materials to hundreds of angstroms potentially, and varying that via the agency of this solid angle just by a sample tilt as the mechanism for controlling that. Now, the thing that you have to understand is that if I tilt the sample, that also has an impact on contrast. And this slide shows you how these profiles might actually go. So if we have a sample with a lot of topology, right? And I would say let's just look at a very one explicit case like that, where we're bringing a beam in this direction along the normal direction, and we're looking at it with a detector which is off to the field of view on one side, right? So we see the secondary electron detector would acquire electrons with that sort of trajectory. And one of the things you notice is that electrons hitting here, emitting secondary electrons, would have to have their electrons, that are coming off with normal trajectories or off in this direction, pulled at large angles to come to the secondary electron detector. Backscattered electrons might actually, in fact, be shadowed by the mountains of high aspect ratio features that are actually in the way, because they'll hit and they'll never reemerge. Whereas backscattered electrons coming off in this direction may actually, in fact, generate more secondary electrons. So the net result being that for all kinds of reasons, this side is going to appear bright and this side is going to appear like it's in shadow. And at normal angle of incidence, this might appear to be symmetric, but also it would actually also be impacted by surface tilts. And what we can see is that if we try to use this kind of protocol where we would take image contrasts and use that as a way of defining both feature sizes and heights, we would actually wind up with information that's a little bit deceptive, because intensity does not scale linearly with height because of these shadowing effects. Okay. And the other part is that because of how we detect electrons, right, and that is we have a primary beam and we have a flux of secondary electrons, the tendency is for the beam to actually lead to detection events that are bigger than the diameters of the beam. And that is we put in a primary beam, there's secondary electrons that come out in the place where the secondary electrons are emitted, but that via all the electron scattering events that we might in fact get via backscattered electrons, secondary electrons that in fact emerge in places that are very much distant from where the proximate beam is, and then the outcome being is that if we detect backscattered electrons or secondary electrons, we may in fact wind up with very much different measurements of the morphological features and dimensions associated with the samples. So with that in mind, we can then go ahead and say, well, what is it that we can see, right? And the really beautiful part is that there's lots of nice analogies with light microscopy, but they do in fact break down. If in fact we use white light, we have to say, do we have high direct normal incidence lighting, or is it from a particular direction, or and what's the field of view associated with our detector, right, which would typically be our eyes in this case. We also have to worry about not only diffuse light sources but also diffuse scattering, blurring image profiles. And whereas with electron-based cases, we have by definition high direct normal incidence associated with the beam as shown in this case, but we have all these topological characteristics that come into play, and we can actually see that in this image. Like there's actually the appearance of shadows, right, that actually show how these spheres supported on a solid substrate are shadowing in a way that looks like, it perceptually looks like, we're getting illumination from a particular side, when in point of fact, this has to do with the particular azimuth that most efficiently captures electrons at the secondary electron detector. Okay. Okay. Now, what's the origin of the depth of focus? And just by borrowing from the analogies with optical microscopy, it really has everything to do with this issue associated with the divergence of the incident beam. So that's shown here in alpha. And let's imagine this focal plane D as shown. This focal plane D as shown here. What we care about is where a feature dimension becomes indistinguishable from the beam width, and the distance d at which that distinction is lost. And so we can kind of see that first and foremost, the narrower the beam divergence is, the higher the depth of view will go. And this actually has really an important consequence for how we might do the imaging. And the other part I would mention is that we have to worry about things related to not only topology but surface tilts as well. Because, for example, here's a beam, here's a sample plane which is tilted relative to the beam axis, and you'll notice that features lying above and below that focal plane will actually have an impacted resolution from both top and bottom related to this loss of clarity due to the divergence of the beam, right? But then we could think about how good might that be, all right? And these are some examples of very high resolution images, but with absolutely, incredible depth of view. So this is, a 10,000 magnification. This is 100,000 magnification. If you look at this example here, okay, this is a scale bar of 100 nanometers, okay? And you notice here this is actually a carbon nanotube. And, and part of what's kind of interesting to note here is that everything that I was sort of mumbling about in the last couple of slides is actually manifested very powerfully in this slide. And the thing I would ask you to think about is the bright region here that's the carbon nanotube. Does that actually correspond to the dimensions of the tube? Actually, yeah, in some sense it does, but the apparent diameter is actually much larger than the diameter of the tube. And even though this is a 100,000x magnification, it just has to do with the fact that the electron emission from the tube is actually being blurred into its dimensional attribute. But the thing that you could also say is that, you know, that's a very long tube, right? And so the depth of view, even like if you look at what's holding this this tube, you know, everything in this image is in focus. All right, here's dendrites, and you can, this is a deposition of gold. I don't know this explicitly, but I'm going to guess because this is something I know a little bit about. This is probably gold that's been deposited electrochemically at a deposition rate which is fast relative to what can be, you know, basically you're driving it at a potential that would make the deposition go extremely rapidly. So it's actually occurring at a deposition rate which is limited by mass transfer. And in those cases, the growth occurs via what's called a fractal-like growth. When we do deposition at diffusion limited velocities, you get fractal-like structures, and dendrites are just, you know, beautiful outcomes of that kind of diffusion limited growth. But again, we see, again, this is a 1 micron scale bar in this case, but we can see structural features down at you know, approaching nanoscale dimensions, but very high resolution and enormous depth of view, right? We're looking at many microns deep into the material, and all this is beautifully in focus. So optical microscopes and electron microscopes do powerful and useful things, but they're very different in the kinds of information you can extract about material structure. You know, this is again another example. You know, just impressive images. You know, that are possible. This is a sample that has been eroded by reactive ion beam etching, and it turned out that this sample had dilute aluminum impurities on it. It's a silicon 100 single crystal, which has been eroded by reactive ion beam etching. It's an ion-based method for chemically gasifying the substrate, and mediated by ion impacts that can basically enhance reaction etch rates. And one of the things you'll notice is that it grew, it kind of looks like, you know, a forest after a fire, you know, these burnt stalks of, you know, former trees standing there on a desolate plain. You know, all the branches and leaves burned off. But actually what these are very thin spiculate architectures that come from the fact that very small aluminum clusters in regions protected this material against etching. And what you do is then anisotropically etch these sharp needle-like structures because of very small clusters of aluminum atoms that had been present at the original interface led to strong anisotropies in what should normally be an etching technique that would completely erode the sample surface. All right, and that's a kind of a beautiful example of high-resolution imaging with incredible depth of view. Okay, so then we should talk about like what happens with regards to other contrast mechanisms. All right, and part of what we can do is to actually construct images which have different ways of doing detection. And so we mentioned that we could do detection with secondary electrons, and we can do detection with backscattered electrons, and we can actually use other approaches for doing the detection. So this is using what's called a secondary electron with a through the lens detector. And this is actually a methodology that uses the E fields associated with the electron optics as a way of screening from the vast majority of backscattered electrons that would actually blur the image contrast using a conventional secondary electron detector. And just to show you that how this can in fact lead to important distinctions, these are two images of the same object. They're both the compound lens system of an insect. I don't know which insect, but let's say fly's eye or something of that sort. And you'll notice that the three-dimensional topology that's present here is very much looks different there. And this is these shadowing effects that we talked about and other contributions that lead to image contrasts that are not height. Okay, and so this illustrates how caution has to be exercised when interpreting information as height that may in fact reflect other properties of the measurement. Okay, now how might we just go ahead and do backscattered electrons? Typically that's done using a charge coupled device, but one actually mounted at the front end of the lens elements that are used to steer and generate the electron beam, right? And this is a depiction showing you an annular detector. So basically all this is a device that allows us to measure currents of electrons coming back in the direction of the electron beam. And if I measure current at this device, then what I'm doing is I'm measuring current that's coming primarily from the electrons associated with high kinetic energies, and whereas most of the secondary electrons are going in one direction, the ones coming back at this detector are largely comprised of high energy electrons. And then we can separate the components of a backscattered electron image from those associated with secondary electrons. And I will mention that there's a really important feature that comes into play when we start thinking about backscattered electrons and constructing images from it. And that is, there's embedded within it a materials constant that really reflects the yields of the electrons that come from different elemental sources. And what you see plotted here, as a function of position in the periodic table, is a measure of what these backscattering cross sections look like as a function of atomic number. And you notice that it has a very strong Z dependence. And as a result of which, this actually provides a way that we can develop images that contain contrasts due to elemental composition. Okay, and here's a really terrific example of an imaging that's done using two different detection means to construct the image. One is a secondary electron image, and it has a lot of topological information in it, right? And these are both, we would say both images say these are relatively smooth samples. It looks a little bit smoother in one case than it does in the other, and that's because the secondary electron image is telling us a lot about morphological and topological information about the sample. And you notice that even with that, we notice within it, splotches, where we have bright regions and darker regions. And when we look at this in terms of the image constructed using the backscattered electron detector, we notice that these dark and light textures are very pronounced. And it turns out that what this is reporting on the elemental content, right, that's present in the image. And what might be, so these are tin bismuth alloys. This is a form of low melting metallic solder. Okay. We can actually infer that by looking at the periodic table by saying, where is tin and where is bismuth on this periodic table. And correctly, and I'll leave that as an exercise for the student to say, what would you say is the tin-rich and the bismuth-rich part of this image contrast? And so with that particular provocative thought, I want to thank you, and we'll return with more in the next sequence of this lecture.